Hi to all. Today's topic is magnetic energy stored in a solenoid. In this solenoid, some energy stores in the form of magnetic. That energy formula I am going to derive. And I am also comparing the energy stored in the solenoid with the energy stored in capacitor. This is the thing that I am going to do. First I am going to derive the magnetic energy stored in the solenoid. Actually, we are connecting the solenoid to the battery. The battery is supplying the current. The battery is supplying the current. Right? When we close this plug key, the current flows. The battery has electrostatic energy, electric energy. Battery has electric energy. When it is plug key closed, that electric energy is supplied to the inductor. And when the current varies in the solenoid, then when some current passes through the solenoid, it will act as magnet. That means at the inductor, what happening? The electric energy converted into magnetic energy. Then who is supplying that magnetic energy? Just the energy conversion is occurring at here. That means the work done by the battery convert into magnetic energy. Just we have to derive the formula for the work done by the battery to pass I current through it. Why? What is the need to do the work? Because this inductor forming the against EMF. Then to pass some current, okay, to overcome the induced EMF, some work should be done. Okay, right. Then work done we can calculate. The rate of work done by the battery. The rate of work done by the battery. The rate of work done by the battery. Yes, the rate of work done by the battery is nothing but power, right? Yes, that is the power formula is, we know that is a work by time. Work by time. You know one formula, power formula in the mechanics, we know that as work by time. But in electricity we know it as voltage into current. Then we write as power formula as work by time. But the work by time, there is a small work by small time. That is equal to power equal to, we know, voltage into current. We can write as magnitude of EMF into, we write as current. This we can write as dW by dt is equal to E formula we write as LdI by dt. We know in the self-induction, right? And this we write like this. And here dt gets cancelled, right? This dt and this dt will cancel. Then we will get the work done to change the di current. Right, that is the formula is LIDI. Okay, right. This is the work done to change the current by DI. But we want to change the current from 0 to I. Right, how much battery will do the work? Initially, when the plug key is open, the 0 current passes through it. Then after fraction of seconds, then the I current passes. Then to change the current from 0 to I, here to change the current by di, this much work is done, and I want the total work done by battery to change current from 0 to I, right? Then the total work means we have to do the integration, that is the integration dW. It is nothing but integration LIDI, but the current changes from 0 to I. Okay, then we have to write outside that constants. Then the work we will get is capital L we write outside integration IDI, that is 0 to I. We know integration IDI formula, that is very simple, that is L into I square by 2, right? I square by 2, that is 0 to I. Then this you got from formula, that is integration x power n dx is equal to x power n plus 1 by n plus 1. And then we substitute the limits, then we will get as L into, in place of upper limit, in place of I upper limit we have to substitute I square by 2 minus, in place of I lower limit we have to substitute 0 square by 2. Then we will get the final formula for the work as half Li square. Okay, this is the work done to pass I current through the inductor, right? And here this work done will stored in the form of, this work done will store in the form of magnetic energy. Magnetic energy. Let us go for the magnetic energy in solenoid. Magnetic energy, right? That means the magnetic energy we denote with U suffix B, that is equal to work done, right? Magnetic energy is equal to work done, because work equal to magnetic energy, right? The magnetic energy is equal to work done. Then what is work done? Half Li square is the work done, right? This is the derivation for the magnetic energy stored in a inductor. Okay, right. Now let us consider this as equation 1, and it is important equation. And now I want the magnetic energy stored in terms of BAL. Then for that we know self-inductance of solenoid. What is the self-inductance of solenoid? Self-inductance, we are taking the solenoid, but the self-inductance of solenoid it depends upon some factors. Yes, what is that? Capital L is equal to mu naught n square AL. And what about the magnetic induction on the axis of solenoid? Can you tell? Magnetic induction on the axis of solenoid. Magnetic induction on axis of solenoid. Yes, that is B. Its formula is mu naught Ni. Okay, we write from this I formula, that is B by mu naught. This we substitute in above equation. Okay, then from equation 1 what you will get? From equation 1, these two you should substitute for the solenoid. That is the magnetic energy is equal, we will get as half L is what? Mu naught n square AL into I square. I is what here you got B by mu naught n whole square. Is it right? Of Li square. This is from equation 1. Okay, we are substituting it here. This capital L and this I formula we are substituting. Then after that you can simplify this. Then if you simplify, we will get some other formula for the magnetic energy stored in the solenoid. You take the screenshot, and I will continue after the rubbing in the left side. Okay, right. Let us see here what we got it here. The magnetic energy UB, capital UB is equal to, okay, UB is equal to half into mu naught n square AL into B square by mu naught square n square, mu naught square n square, right? Now we can simplify, we can cancel something, right? This is n square and n square will cancel. This square and mu naught will cancel. What's remaining it here? That is the magnetic energy stored formula is B square into AL by 2 mu naught. Okay, this is the formula for the magnetic energy stored in terms of BAL. One time they asked the question, that is derive the magnetic energy stored in terms of BAL. B is the magnetic induction, A is the area of cross section, L is the length of the solenoid. Okay, this is equation 2. What is B in this? Magnetic induction on the axis of solenoid. On the axis of solenoid. Okay, right. Or instead of solenoid, actually magnetic energy stored in the inductor we are deriving, na? Right. Magnetic energy in the solenoid or the inductor we can write. And here A is the area of cross section. Area of cross section. and L is the length of solenoid. L is the length of solenoid. Okay, right. Solenoid or the solenoid with high coil with high inductance is also called as inductor, right? Inductor also we can tell, no problem. Okay, right. And here I want the magnetic energy stored per unit volume. Magnetic energy stored per unit volume. Per unit volume. Okay, you have to divide with volume, that's all. What is its volume? Can you tell volume of this one? Volume is equal to cross sectional area into length, is it right? Yes, the volume is cross sectional area into volume. That the magnetic energy stored per unit volume we can denote with a small ub. It is equal to, right, magnetic energy by volume of solenoid. Magnetic energy by volume. Yes, magnetic energy by volume. Magnetic energy by volume. Okay, right. Then UB is equal to, what is magnetic energy? B square AL by 2 nu naught by volume. Volume is what? Volume is equal to cross sectional area into length. We write here AL. This will cancel. Then finally the magnetic energy stored per unit volume we will get as B square by 2 nu naught. B square by 2 nu naught. Okay, this is equation 3. This is the magnetic energy stored per unit volume. Magnetic energy stored per unit volume. This we can compare with the electrostatic energy stored in the capacitor. Magnetic energy stored per unit volume is proportional to B square, right? Electrostatic energy stored per unit volume. Electrostatic energy stored per unit volume. Per unit volume inside the capacitor, in capacitor, right? Then what is that? Already we derived in case of capacitor, right? Its capacitance is C, and if the space between the plates is vacuum, then magnetic energy stored per unit volume, electrostatic energy stored per unit volume is UE is equal to V gata as in the first chapter we discussed, right? Of epsilon naught A square. This from this we write that is electrostatic energy proportional to square of electric field intensity, right? This is the equation 4 and this is the equation 5, right? And magnetic energy stored per unit volume. Magnetic energy stored per unit volume depends upon magnetic energy stored per unit volume. Stored per unit volume proportional to what? Square of magnetic induction, square of B, right? And what about the electrostatic energy stored? Electrostatic energy stored per unit volume. Per unit volume proportional to square of E. E is the electric field intensity, right? Okay, and this is about magnetic energy stored per unit volume. Thank you for watching my lectures. Share and subscribe my channel. If you have any doubt, you can ask me in the comment box. Thank you.